In this video, we're going to look at the concept of called finite differences, specifically looking at sequences that are based on first-degree polynomials. Now, if you're asking what a first-degree polynomial is, you're familiar with it. It's just a linear-based relationship, meaning y equals mx plus b, except our equation is going to be written as t sub n, the nth term, is going to equal an a, which is taking on the role of rate of change, times n. It won't be x because we only want integers for our term numbers, first term, second term, third term, so on, plus b, which really just still means like a starting value, assuming n was 0. But our sequences are going to begin with 1. What's interesting is it doesn't matter what the sequence is, as long as it's based in a first-degree polynomial, there are certain things that we can always expect. Let me give you an example. If we plug 1 into n, we would always know that the first term is going to be a times 1 plus b, which I'm going to write here as a plus b. So it doesn't matter how you start your sequence. Whatever number you have is going to be the sum of the two values a plus b. If we go to the second term and plug 2 into here, what we would be coming up is 2a plus b. And we could go down the line and realize that every single term of the sequence is going to be with n filled in. So we got a plus b, then 2a plus b, 3a plus b, so on. What we're interested in is how those terms are changing. What is the difference between the first term and the second term? What is the difference between the second term and the third term? The easiest way to find a difference is to subtract. So what I want to do is I want to go 2a plus b, and I want to subtract a plus b. How did it change? Well, really, all I did was add a to the first term to get to the second term. And then I realize I'm adding a again, and a again, and again, and again. It is this part here that makes up our finite differences. A few videos ago, we would have called this the common differences. And we can do that because it's a first-degree polynomial. Now let's take a look at the sequence vertically and notice that the common differences, which we're now going to refer to as the finite differences, are located here. The key to understanding what's going on is to understand that this particular column has to sync up with this particular column right here. And since every one of those values is 6, just like in the chart down here, every single one of those values is a, I can now say that a must be 6. And if I plug that into my formula, I can start establishing that it's now 6 times n plus a b. But you'll notice I have a plus b equal to 13. Where did that come from? Well, in this case, it came from this value right here. This 13 happens to be in the same spot as this a plus b is right here. Therefore, a plus b must be 13. But I know a is 6. And because a is 6, I can go 6 plus b is 13, and I can use that to figure out that b is 7. Once I realize that b is 7, I have both terms, and I can come up with a formula that specifically says t sub n equals 6n plus 7. Now, if I were to ask you what the next term of the sequence is, you could do this recursively. I mean, you could, if you wanted to, realize that if I added 6 each time, I would get 49. You could then go ahead and do it again to come up with 55. On the other hand, if I want the 55th term, do you really want to do this recursively? Probably not. Smart play would be to take this explicit formula that you generated up here and say 6 times 55 plus 7 gives you 337. And this is the process in which we generate an explicit formula for finding these particular types of sequences that are based in first degrees. So let's start this whole process all over again with a new sequence of 9, 17, 25, and so on. Let's sync up our numbers. So we go 9, 17, 25 vertically. And then let's realize that 9 plus 8 gives you 17, 17 plus 8 gives you 25, and down the line. What I'm going to do is I'm going to sync up my charts top and bottom, and I'm going to just focus on the top sort of diagonal. That's all you really need to do when figuring out these problems. And I would start specifically here at this end right there and right there, because that gives you your first letter. It gives you a value that A is 8, which now you can plug into your formula and say 8n plus b. So now you can take the fact that 9 has to be equal to a plus b, substitute 8 in for a, and you'll realize that b happens to be equal to 1. Okay, so if I wanted you to find the next two terms of the sequence, let's do it one at a time, okay, you might come up with 57. But how would you have done this recursively? Well, you would have taken 8, added it to 49, and came up with 57. If you wanted to get the next term after that, which is 65, you would add 8 to the 57 and come up with 65. Or you could just do this explicitly. You could stick in, let's see, this was the 8th term. You could go 8 times 8 plus 1 and say 65. In fact, that's how I'm going to find my 39th term. It's a lot faster to do that here. So here we go. I plug in 39 times 8, add 1, and lo and behold, I come up with 313. Let's do one more problem really quickly. Except let's look at values where the sequence might be decreasing. In this case, -2, -11, -20, -29, -38, -47. Remember, it is a difference between the second term and the first term. So don't go -2 minus a -11. You need to go -11 minus -2. You're going down. Therefore, you should expect the common difference, or our finite difference, to be -9. And it will stay -9 throughout the whole process. So we can then quickly establish that this a and that -9 are one and the same. We can plug the -9 into our formula, realize that -9 plus b has to equal -2, and then solve that b has to be 7, and come with the formula -9n plus 7 is going to equal our nth term. If you would like to come up with the next term after -47, which I'm doing here, I will get -56 if I add a -9 to a -47, and that's how I'll get -56. Just like if I add -9 to the -56, I'll come up with a -65. If you'd like to get the 47th term, go ahead, plug 47 into your explicit formula here. -9 times 47 plus 7 works out to be -416. Or feel free to do it 46 terms before that point.